and then yes, of course, you can share your screen. Good afternoon, everyone. It gives me a great pleasure to introduce one of our current student from Georgia Tech, who works in Trust 3 Task 3.1 with Professor Sam Gogan. Christian received his PhD degree in aerospace engineering from Embry-Riddle Aeronautic University in 2019.
A Bachelor of Science.
A bachelor. What did I say?
Yeah. PhD.
Oh, sorry. What is going to get? Okay. All right.
Almost there.
Yeah, he's currently pursuing a PhD in robotics with a MS in the aerospace engineering from the Georgia Institute of Technology. His research interests are in optimization, stochastic systems, robotics, and aerospace application. He is currently working with the formal methods and autonomous control of transportation system lab at Georgia Tech. With any further ado, Christian, you could start your presentation.
Great, thank you. So I want to thank everybody here for coming to this seminar talk. My name is Christian Llanes, and as Abdullah said, I'm a second-year robotics PhD at Georgia Tech, and I'm working with the formal methods and autonomous control of transportation systems lab. And my advisor is Dr. Samuel Coogan. And the work in this talk is a joint work with my advisor and Matthew Abate, which is a PhD student in my lab. And the title of this talk will be Safety from in-the-Loop Reachability for Cyber-Physical Systems.
For you, okay, the recording starts. Okay.
Oh yeah, recording. Okay. So for this talk, I'll first introduce the objective, which is the main purpose for why this work is relevant. And then I'll give a small little review of what a controlled dynamical system is, as it's a prerequisite for the rest of the work in this talk. I'll then introduce the notion of runtime assurance, which is a tool used for ensuring safety of a controlled dynamical system. And this will be more like a high level, and the rest of the talk will go over the tools used to construct the runtime assurance mechanism. And then I'll give a brief discussion of control barrier functions because of their extensive role in our runtime assurance methodology. And I'll also state why using classical control barrier functions alone, they're not enough for controlled dynamical systems like quadrotors, and this will also lead to introducing like disturbances. And in our final theoretical discussion, I'll provide our algorithm for runtime assurance with reachability. And then at the end of the talk, I'll provide a little case study that uses our runtime assurance algorithm to guarantee that 2 quadrotors avoid a collision with a hardware demonstration where we compute reachable sets and verify safety on the control loop at 100 Hertz. So now the objective of this talk, it's to discuss safe, assured autonomy for controlled dynamical systems. And these systems can be thought of as autonomous urban aerial vehicles, such as the Urban Aerial Mobility Effort on the left from NASA, or the Uber Autonomous Car Project on the right. And these are only 2 examples of many where really safety violations can result in complete failure of the vehicle. So there really is a need for safe, assured autonomy for systems of this class. And so in this slide, I'll give a little bit of a review of the structure of a controlled dynamical system. And we're only really looking at continuous systems with defined control inputs in this talk, where the state evolution is really continuous in time, as opposed to discrete or hybrid, where systems were possible switching mechanisms. And so if we look here above system dynamics, we see some equations, an ordinary differential equation with another mapping equation from x, which is the state, and sort of these can represent position, velocity terms for a vehicle, and the y, which represents the outputs. These can be sensor measurements, and these can also be corrupted from some noise sometimes. This is introduced in the formulation. And so the system dynamics produces some outputs, which are measured from some sensor. And then you have some estimator, whether it be a particle filter or a common filter. This estimation, if there's noise introduced into the sensor, then the estimated state is not exact, but if there's perfect world, then you can inherently map from the output y to x using the inverse of h. So then if it is noisy, then you get some x hat, which is the estimate of the state, and you feed that to a primary controller. This is what's going to be controlling your vehicle to do some kind of objective. And this primary controller can be like using model predictive control, PID, linear quadratic regulation, or neural network. And so this will give some control, desired control action that meets some objective, and that is fed to your system dynamics, which is the vehicle. Braking on a car, or gas on a car, or thrust on a quad rotor, et cetera, et cetera. So what happens when the controller is unsafe? And well, in a large scale, your fleet of aircraft are grounded. They might be grounded because of numerous accidents that may have occurred, or on a smaller scale, you have UAV, your UAV crashes into a tree. And if we want to operate in an urban environment, then we really need to make sure that this does not occur. There's a lot of buildings, traffic, and a vehicle falling down and hitting somebody would be a total loss, and we would not want that in an urban environment. So one possible solution to this problem is a runtime assurance mechanism. And as in the previous slide on controlled dynamical systems, we now place an assurance mechanism, as you see here, or a supervisor over the primary controller to ensure the system does not crash. And one method of designing the assurance mechanism is to switch to a backup controller when you're unsafe. Now, the problem with this is if you switch too late, you might be unsafe anyway. So you need to formalize some decision module to make sure that you're switching to a backup controller at the right time, very specifically. And that can be non-intuitive to design, and there could still be faults. You can still have some chattering in the switching from the backup controller to a primary controller. Yeah, so in our approach, actually, what we're going to be using is control barrier functions. And this allows us to minimally adjust this desired sort of controller to give some safe controller that is as close to desired as possible, but is safe. So that is what we're going to be doing. And we're going to be using control barrier functions. And what they are, they're a mathematical formulation for specifying safety boundaries. So if you're approaching some unsafe condition, then a good way to express safety is to continuously slow down. And that rate that you slow down is dependent on how close you are to unsafe. This is kind of like if you're braking in a car. Sort of humans intuitively understand if you're approaching a stopped vehicle at a red light, right, then you press on the brakes. But the force you put on the brake pedal is dependent on how fast you are and how close you are to the stopped vehicle. And this is really analogous to the control barrier functions. So a barrier function is a function that for some given safe region, the boundary is equal to 0 and everything that is safe is positive. So if you see this little example on the bottom, you'll have this, we have this function h of x is equal to 4 minus x1 squared minus x2 squared. You can consider x1 and x2 to be position states, position in x and y of the vehicle. And so safety is defined by, if you plot this in, and the vertical axis here is the h of x, which is our barrier function, then you notice that all positive terms are within this sort of this region enclosed by this circle. And this is essentially saying that you're safe if you're within this circle, and everything outside of it is unsafe. So the boundary that splits the safe and the unsafe regions is when the h of x, or the barrier function, is equal to 0. And then again, safety is when you're in the positive. And in the given equation, there's a set of all possible control actions here. These are all the possible control actions that are actually feasible to ensure that your system remains safe. So if we break this down here, we have the set of all possible control actions, right? All possible control actions in this case, say you can do all of R of M as a vector, right? But it needs to satisfy this inequality. That is this strict requirement for control barrier functions. And what this is on the left side is the time derivative of the barrier function. So say you're traversing towards the unsafe region, right? Let's say you're at the center and you want to move towards the unsafe region because you want to explore. Well, your time derivative of your barrier function would be negative, right? But as you get closer and closer and closer to the red sort of circle, the unsafe region, this you can define this how fast to slow down, how fast you are allowed to continuously go to the unsafe region. This is defined by this strictly increasing function. So you're essentially lower bounding how fast you are allowed to continuously go towards the unsafe region. And this can be simplest form would be like allowing alpha to be a coefficient and multiplying by some term of h of x. So as you approach 0, you're lower bounding essentially the rate of change by 0. So as you get closer and closer and closer, you're allowed to go negative towards the negative side of the time derivative of h. It sort of approaches 0. So you pretty much are specifying that you're slowing down as you approach this unsafe region. So this is great, but now how do we use that sort of the previous formulation in a way that really ensures some primary controller doesn't violate a safety constraint? So now is when we dive into runtime assurance with sort of control barrier functions, or CBFs for short. And CBFs can be constructed in the form of a closest point optimization problem, where this reference point is the desired control action, as you see the U to D of x, at some instant in time. So let's say you want to run this whole thing at 100 hertz. Every instant in time, you solve this optimization problem, which is a closest point problem, and you're essentially minimizing, you're finding the argument that minimizes this difference two norm between what you actually are solving for, this optimization variable, and what the desired optimization variable or control action is. And this U has some constraint, and that is the constraint that I showed you in the previous slide. It needs to be contained in the set of possible control actions, essentially. So that is what you're solving for. And now, if we apply this to a quadrotor example, just a two-dimensional basic quadrotor example where the objective is to go from the point -2 to 5, where there is a wall in between at somewhere between 3 and 4, then the vehicle will, in the real world, crash when it hits the wall. And so in this unsafe sort of condition where this active set invariance filtering algorithm is not present, the vehicle will crash. But now, with using this supervisory control methodology, we essentially have the vehicle slowing down and stopping before it hits the wall. So even at this point where it's at 3, the primary controller is still telling it to go to 5, but the supervisor is telling it, no, there's a wall, so I can't keep going. That is what's essentially going on here. And I can also demonstrate another example where, say you have some vehicle in a corridor. In this case, it's going to be a quad rotor. It's within some corridor, this green rectangle, and it's allowed to sort of traverse only in this rectangle. And the objective is to go from the point 0, -1 to the other side of the rectangle, 0, 2. But now, well, the ideal path would just be a straight line. But the problem is that some obstacle is going to come into the path of the vehicle, and one of the safety constraints is going to be that the vehicle is not allowed to be within a certain distance of the obstacle. So now if I play the simulation, you'll see that the vehicle turns back as the obstacle comes into the path of the vehicle inside the corridor. And as it clears, after it clears the path, it goes freely because it's now safe to continue on. And so using control barrier functions in the way discussed in the previous slides, now they can result in a few problems. And the first issue is control constraints. If your vehicle or dynamical system has actuator constraints, such as the upper and lower limits of a quad rotor thrust, or the braking power of a car, then control barrier functions may not provide a viable safety controller. And for some problems, the control action requested by the CBF really it's out of the range of the possibilities because you're saturated. You can't produce more thrust than you have in the real world. So a lot of the real world systems have actuator constraints, and using control barrier functions, they may not guarantee safety. And another problem here is the relative degree. So the relative degree of a dynamical system, in a high level, this is like having a quad rotor that has some horizontal velocity directly towards, say, the wall, right? And if you define the barrier function as the distance to the wall, then your control barrier functions, that would not provide a safety controller. And this comes from the fact that you cannot slow down without first pitching the quad rotor to the left. At that instant in time, it's not possible to give you some control action that changes the rate of the time derivative of the barrier function. No possible controller can instantaneously change that barrier function because you first have to pitch to the left to be able to clear or slow down. And that is one of the issues with this relative degree problem. And that is when so the system dynamics doesn't have a well-defined relative degree. That is what we call it. And a possible solution to the problem with classical control barrier functions is to consider a verified safe subregion. And it's usually more conservative. And it can be constructed from a Lyapunov-like equation from, say, closed-loop backup dynamics. And at some instant in time, you run a simulation of the backup controller to ensure your safe region is within reach. And this addresses the previous two problems because control constraints can be expressed in the simulation of the backup controller. And you're now considering what happens in the future if you use a backup controller, which means we fixed the relative degree problem. Also, since the backup controller is verified to always bring your vehicle back to the safe subregion, then we can always ensure we're safe to leave this safe region as long as this backup controller can take us back within a fixed time window. So we set a time window, some time horizon, we simulate the backup controller, and if it takes us back to the safe subregion, then we can continuously keep going until sort of the end point sort of starts reaching the boundary. And that end point is what sort of comes into play as as you saw in the previous sort of equations of the optimization problem. So in a mathematical perspective, I'm going to introduce a few extra sort of variables here before I sort of go into the math of the ACIF formulation. First variable is going to be phi superscript b, and this could be the trajectory using the backup control policy. So say I have that backup control policy, I apply it to the quad rotor for a specific amount of time, t, capital T, which is your prediction horizon, then I'll get a trajectory. And this will be parameterized by time and the current state that you started at, which is x. So this will give me essentially sort of like a vector of all the states that I'll be at throughout the trajectory. And I can then use that to define this new term called psi of x. It'll be somewhat replacing this h of x, as in the previous formulations of classical control barrier functions. So now what we do is we take all the states and the trajectory with the backup control policy, and we evaluate what the barrier function is on each of these points. And then we find what the maximum is over all those computed barrier functions throughout the trajectory. And that'll give us what psi is. And the argument that maximizes that point is going to be t star in this case. So then really now this implicit ACIF formulation, we then use the classical barrier functions optimization problem, but instead of h, now we use psi. And since psi, we're going to need to use the chain rule in this problem. And for this term, you find the right term is going to be essentially the Jacobian of the state dynamics, evaluated at that maximized time T star, and then the partial of the barrier function over the states evaluated at that state that was the best case. So this whole sort of combination of tools will allow you to sort of fix those two problems that we discussed, and in a similar fashion, using the control barrier functions sort of optimization problem. So now we can cover this section of safety from in the loop reachability. This is like a continuation of the previous slides on control barrier functions and implicit ACIF, but now we introduce reachability, which comes in from adding some disturbances to the dynamics. So if we really now add disturbances, some bounded disturbance to this quadrotor simulation with the ACIF that I showed you before in the previous slide, you see here that this vehicle is not safe anymore because the disturbance is not taken into account, and there are large disturbances, and eventually the vehicle crashes into the wall. And so if I were to use, say, implicit ACIF with some small verified subregion that, like I said before, and if it were to be guaranteed to be safe, even with disturbances, then that small subregion, we'll call it a robustly forward invariant subregion. So we need to make sure that for all possible combinations of the disturbance, we're guaranteed to be within this safe subregion. And the major problem is that computing reachable set, or the set of all possible states you may end up in, for all possible combinations of the disturbance is expensive. As in the cartoon on the left, we have this safe and invariant subregion in green, and we're allowed to traverse the blue line if the reachable set, this pink box you see, if it's fully in the interior of the safe region, even if a corner is outside, we're unsafe. There's a possible condition where some possible combination of disturbances will lead you to be on this outside of the safe region. Not that it's unsafe yet. This unsafe is defined by the red. It's just outside of the safe and invariant region. We're not verified if there's a point that is leading you outside of the safe and invariant region. So nominally, some primary controller is taking you to the red region, to the unsafe region. But then if you have this safe and invariant region and you choose some prediction horizon that will ensure that you never go into the unsafe region, then you can always follow outside. You can traverse the outside of the safe and invariant region because you know that even for all possible disturbances, you have a path back to the safe and invariant region. So as stated, computing reachable sets, it can be expensive and not feasible in the loop when you're requiring fast update rates. It could take seconds, minutes, it could take hours. So what's the solution? Well, now mixed monotone systems, they're a generalized class of nonlinear systems with efficient reachable set computations. And this generalization to a class of systems is not actually very restrictive because actually all locally Lipschitz dynamics are mixed monotone. In the following slides, I'll discuss a bit about mixed monotone systems. And so here we consider this autonomous non-deterministic system. X dot is F, X, and W. Or X is it could be in this set of states X, and W is the disturbances. And the system is said to be sort of mixed monotone if its vector field can be decomposed into increasing and decreasing components. Or in other words, if you can find a decomposition function, some function D, that satisfies these four conditions in the slide, then it's a valid decomposition function for your mixed monotone system. There may be multiple decomposition functions that actually satisfy this condition with varying levels of conservatism in the true reachable set. In the next slide, I'll show you how this decomposition function is used to find an over-approximation of the reachable set. So first, we construct a 2 times n dimensional embedding system from the decomposition function. And say, for example, in 2 dimensions, the value of n is equal to 2. And so the first 2 entries can be thought of as the lower left corner of a rectangle, and the last 2 entries are the top right corner of this rectangle. And this is generalized for multiple dimensions for like a hyperrectangle and the embedding system. And so the embedding system is actually monotone with respect to something called a southeast order in the embedding space. And what the southeast order is say you're given a tuple of x and x hat and y hat, then if x is less than or equal to y and y hat is less than or equal to x hat, then this condition is valid. And this can be visualized in 2D as well as sort of x being the lower left corner, x hat being the top right corner, y left hand lower left, y upper right. And now if x and x hat is less than or equal to y and y hat with respect to this southeast order, then y hat is fully contained in this rectangle of x and x hat. So one important detail we're assuming is that closed loop backup dynamics, they're mixed monotone with respect to a decomposition function. And this enables us to use the backup controller as is needed in the implicit ACID formulation that we discussed previously. And at each point in time, say you're running at 100 hertz or 250 hertz, you simulate the embedding system for a fixed prediction horizon. And this provides an over approximation of the reachable set. So what mixed monotonicity does, it converts a reachability problem, which can take seconds or minutes or even longer, and you're trying to do this in a loop. Now what you do is you're solving this continuously as an ordinary differential equation, which is way more computationally attractive than previously using brute force. So in the figure, you have a small little example here where in red you have, say, all possible initial states you can be, and in darker green are the true reachable set simulated. It could take up to a minute to simulate this. But in light green, you could take less than a second, much, much faster, but it's an over approximation, right? And you can have various levels of conservatism. Say you have, oh, wow, that's actually a lot of states you can be at, but there are sort of other tools published already where you can use sort of higher fidelity approximations using transformations. And you can get approximations that are tighter, such as the one on the very right here. Now for the algorithmic overview. So as in like the previous implicit ACID, if I went over the mathematical representation, essentially this formulation with disturbances in the reachable set, it's very similar. What you do now is for the entire trajectory, you evaluate the worst corner. So in this point, you have the worst corner is the top right corner because it's the closest to outside of the safe and invariant region. So it's really the minimizer. You find the minimum of the barrier function over this entire set, which what you can do is actually, because of the nature of the way that the barrier function is defined and is a hyperrectangle, you can evaluate each corner, which in this case in 2 dimensions, say it's 4 corners, but in multiple dimensions, it's 2 to the n. So you evaluate all the corners, and the one that's minimized, that is the one that you are evaluating to. Now you do this for the entire trajectory. At each instant in time, you have some hyperrectangle. You evaluate the corner, evaluate the corner, evaluate the corner for the entire trajectory, and then we do this maximizing step. That is when we do the maximizing step. Not over the barrier function, just strictly h. It's over what evaluates to the worst corner on the rectangle. And so this can be kind of expensive if you sort of do over the entire trajectory uniformly, because actually if you, let's say it's some previous time step, you know what sort of T star is, right? So if you know what T star is, you can actually figure out what your new T star is going to be, or you can approximate it because you know it's going to be continuous and it's going to be close to what it was before. So instead of using a uniform distribution to compute sort of the minimum barrier function over the entire sort of hyperrectangle over the entire trajectory, then you can do a log-based distribution. You cluster more resolution close to where T star was before, and you get a better approximation of where your next step evaluates to. You get better resolution and better performance if you do use this log-based distribution. Otherwise, you would have to evaluate so many more points that are not necessary in the algorithm, and this allows us to sort of run at these higher rates. So now I'm going to go over that was pretty much a final algorithm overview of our algorithm, and now I'm going to discuss a hardware demonstration of our algorithm for a dual quadrotor case study. So we have two multi-rotors, and they're fixed to the YZ plane. And say we inject an unsafe controller that leads to a collision. And this controller, say you initially start this vehicle here and this vehicle here. And the primary controller, this unsafe controller, is telling both vehicles to come together at this point, this center point here. That would lead to a collision. But now we need to supervise this and ensure that they are within some safe displacement in delta Y and delta Z. So the goal of the implicit ACIF filter is to filter those commands to avoid this collision. And we're defining a safe distance to be 1 meter in displacement in delta Y and delta Z. So like I said before, we need a backup controller as originally in the implicit ACIF formulation. And the backup controller that we're going to be using is essentially considering what happens if there's a spring in the Y and Z directions. And this spring is going to saturate. So we're going to have a saturated spring, and then we're going to have dampening terms in the velocities and the Y and Z velocities of each quadrotor. So that'll produce forces in each of the cardinal directions. And here are the dynamics of the dual multi-rotor system. And then if you have the backup control forces, you can plug these into these equations, and you'll get the backup controller thrust and body rate commands. So tau is going to be the total thrust of the vehicle, and then W is going to be the body rate in the X direction. So essentially the angular rate of these two vehicles. So that together will give you the entire backup controller, and you can close the loop, plug these into these dynamics, and you'll get closed loop backup dynamics with respect to the states only. And then you can also find a safe and invariant subregion, which we did with a Lyapunov-like equation. Now for the hardware, what we use is we use a custom build where we use a Jetson TX2 connected to a Quasar TX2 carrier board, and this will be running Ubuntu TX2 Linux 2004. And then this will also connect to a smaller computing power flight controller, and this flight controller will do everything related to low-level control, controlling like the electronic speed controllers, the motors, all the communication, and sensors, estimation, everything related in that form will be done on this flight controller, and this will be connected with the Quasar board, the Jetson TX2. And so for software, what we're going to be using is ROS2. So ROS2 on the Jetson TX2, that will be running our main algorithm, because our algorithm requires so much computation that a microcontroller cannot handle. But it's fast enough, and there's very little latency between the carrier board, the onboard computer, and the flight controller. And so the ROS2, as I stated, there are going to be multiple layers. So first, we're going to have ROS2. So we use OptiTrack. These cameras are going to be using for localization of the vehicles. Those will provide position estimates that then an extended Kalman filter provides the states. And these states will get fed back to the Jetson TX2, which is our node uses, our algorithm uses. And so initially we're going to have the position controller. This position controller provides sort of the unsafe control actions. And then those are fed directly to a node that is called mav-ACIF. And that is our implicit ACIF formulation, that our algorithm. And that computes the reachable sets. It does all the barrier function evaluations, everything. And then that is what gives control commands to some other node that handles all the communication with the flight controller. So this cascade is very similar to the control dynamical system cascade block diagram that I showed in slide 4. So here we're going to have a little simulation on Gazebo, and it's going to show that in red is the unsafe, well, they're both going to be provided an unsafe control action, but in red is without our algorithm, and in black is going to be with our algorithm. So you can see in red, the bottom right vehicle collides with the top left vehicle. But with our algorithm, they both almost centroid. The centroid of these two vehicles is almost the objective. They're both trying to reach this point, but they're sort of still safe a distance apart. They're still within the safety boundary that I'm provided. And in the next slide, this is the hardware demonstration where you saw sort of like the black trajectories that I showed in the previous simulation, where they are safe. And this hover point here is where they both want to meet. See, now I'm returning them back, and let's play this again. They're both where their initial positions are, and this vehicle is commanded to this vehicle location, but now it's avoiding it. See, they're both now centered around this point where they both want to be, and they're a safe distance apart. So now here is the data for this flight. And two things I want to point out. On the left-hand side are the control actions. In red is going to be the primary controller. That is the unsafe control action that I'm providing. And in blue is going to be the filtered control actions from sort of passing through our algorithm. So previously, before the unsafe controller is activated, you can see our algorithm is active, but it's already safe. So it acts as a pass-through. It's allowing it to go through because it's already safe. But then the unsafe controller sort of comes in, and it's initially allowed to explore a little bit until it starts to get a little too far away from, a little too close together. And so now it's starting to get filtered. And you see a disparity between the two controllers. Now, because it requires some activation to ensure safety. And you can see on the right-hand side, we'll have the states, delta Y and delta Z, which are the displacement states of the two vehicles. And in green is the safe region. This is a safe subregion that I talked about in implicit ACIF. And in blue is the reachable set lower left and top right corners. And in orange, you see here the reachable set. So this reachable set is fully contained in the green. So it's allowed to keep traversing. But as it gets closer and closer to the boundary, it has to keep slowing down. So now here's our algorithm execution time. So the execution time for our algorithm has the highest frequency of occurrence in the 2.5 to 3 millisecond range. And you can see that in this histogram, where the histogram is plotting execution time versus frequency of occurrence. So the main things are that we're computing reachable sets from this simulation of the embedding system. So we're solving this ODE. Then we're computing the barrier function over 2 to the n corners of the hyperrectangle, solving sort of 2 to the n linear equations. And then we're solving this optimization problem that I discussed. And we can do that up to 250 hertz. We only really do it at 100 hertz because it's all we need, but we can still do it at 250 hertz. So some primary controller that runs at 250 hertz, we could filter it out. So that is the main strength of our algorithm, and we can do all this on a small onboard computer. So some concluding remarks. Control barrier functions, they can be coupled with a simulation of the backup controller to increase usability. And for a system with disturbances, the prediction is a reachable set, and we can use mixed monotone systems for efficient reachability computations. And then 3, we can, this implementation, we do it on embedded hardware, and we're able to achieve combine these techniques to achieve really fast, high in-the-loop reachability analysis with formal safety guarantee for this dynamical system with disturbances. So that is the end of my talk.
Thank you very much, Christine. Okay, very informative talk. Thank you. Okay, any question from Christine? Okay, while others are thinking in the cyberspace, what are the major characteristics of this barrier function that you mentioned? Are you assuming that barrier functions are smooth?
Yeah, I mean, it's just it's an actual function in itself, right? It's not some discrete.
No, are you assuming smoothness?
Yes.
So convex, basically, you're assuming these barrier functions are convex?
Right. Well, actually, not convex. No, it's actually concave in this example here.
Okay.
It's not, but the convexity is not like it's not anything to do with solving the optimization problem in itself. The optimization problem is convex. The smoothness is like you don't have any switching. So as in like the simplex architecture where you have switching to a backup controller at some particular time, you have some jump in the controller. This doesn't occur in this problem because what we're doing is we're solving this optimization problem. And as it starts to get sort of closer and closer to the unsafe or the boundary, the region, then you slowly start to alter the control action that is desired.
Basically, what you're saying is you have two control action. When it comes to switching, you know how to switch it, basically. Basically, both control actions are on, and you don't need any switching, basically. This is what you're saying.
Yeah, there is no switching. Like, it doesn't switch to one controller to the other, actually. Like, what you're passing, it'll pass through, it'll basically smoothen out. It's almost like a smooth version of the simplex architecture. It's almost like that, but it's not really the same theory. Yeah.
Okay. And then, do you require a very tight controller as well when before reaching to the boundaries?
So when it starts to reach the boundary, it really depends on how you define this strictly increasing function. If you define it to be very less aggressive, as it gets really close to the boundary, it'll start to request sort of these large control actions that'll make it safe. So that was the case where I said that you can have this case where your control constraints have to come into play, or you have to tune this strictly increasing function to give you sort of a better smooth curve, so that you don't request at the last minute. At the last minute, you don't start to switch to start doing safe actions. It'll do it ahead of time.
Remember what Jules asked you, the question about whether the barrier functions can adapt themselves? Basically, here you're assuming
the barrier function doesn't actually change in this problem. No, yeah, I remember that question. The barrier function doesn't change. You define this a priori, all of this a priori. You define it. Yeah.
Then, do you mean that you know about your reachable set, that that's how you are defining your barrier function?
The barrier function is defined by sort of in this little example here, let's say you want to stay within this circle, right?
Mm.
So in this circle, you want the most safe portion to be the center of the circle. And the outer part of the circle would be somewhere like 0. It should evaluate to 0. The center should be the highest point. The edges can be 0. And this function provides that for you. So it'd be a valid barrier function to be used for your formulation. And in this simple classic CBF example, in this very simple classic CBF example, you can find a barrier function however you like. You can also run into these relative degree problems as well, depending on how you choose the barrier function. But it's also, yeah, there's a lot more to sort of this theory you also need to consider.
Okay. Thank you. Thank you very much. Okay, any question from Christian on the cyberspace?
I have a question. Sorry, Mehran is speaking. Is it possible to make the safety region time varying or changing frequently?
So you need to verify that the safe region is actually safe a priori, because it, like,
Means what?
so let's say that I define, let's say I have a backup controller. Let's say in this little example of implicit ASIF, right? You have some smaller verified safe region, and you have a backup controller. So in our case, we use this backup controller, right? These nonlinear springs. If you plug these into these equations, you get closed loop dynamics, right? Dynamics are with respect to states. There's no more inputs anymore, right? So you have closed loop dynamics. So you find a valid Lyapunov function that is valid for the nonlinear system. So you have to find a sort of a set that is forward invariant, that is a valid Lyapunov function, and then you construct a barrier function out of that Lyapunov function. So you had to do all that stuff before to find that forward invariant set.
Okay. So it's very much limited to. Okay, I understood. Okay.
Yeah. So the safety, like, you would know a priori what the safety is, right? So there's really no need to change the safety problem anymore. It's almost like you're saying, "Oh, now my safety problem is to do this instead."
You cannot do that.
Yeah.
Okay. Yeah. Okay. So it's a common approach to use Lyapunov to these kind of problems. Thank you.
Yeah. To construct that safe subregion.
Okay, you mentioned that, but what about the computation? That can you put a small computer in the drone that you mentioned, and you do all the computation?
Yes. Yes. I mean, this Connect Quasar is a carrier board.
Mhm.
You have a Jetson TX2 module that has the CPU, the GPU, all the processing. You connect it to this board, and this combination, you can use all this combination to sort of compute everything that we just talked about. This little small board you see on the left, that is doing all the computation. I'm not doing any off-board computation on a laptop or anything. So you can take this outside and then run this type of algorithm.
Okay. Thank you. Okay. Any other question from Christian? Okay. If not, we're going to thank Christian. It really was a very good presentation. Thank you. And I hope other students also take this as a guide of how detailed